Hi, welcome to StatStuff. I'm Matt Hansen. Well, by now you may have gone through a lot of different hypothesis tests from the analyze phase. And if you're running a large project with a lot of complexity in your analysis, your head may be swimming from the many results and all the hypothesis tests and findings that it makes it difficult to make sense of it all. Well, in this lesson, I'll show you how you can take all those test results and compile them in such a way to help you synthesize your results and hopefully make a little more sense of it. So let's jump right into it. So why is it that I should compile all the statistical test results from the analyze phase? Remember, there's a lot of tests that you're running. In order to validate your findings with your team, you don't want to necessarily go through all the numerous details of all the variations of the tests you might have run based off of the data that you collected. So you might find yourself boring them by scrolling through all the items in the session windows and outputs and charts that you might have created within Minitab or even from within Excel to review all the details of your analysis. So it's a better way to maybe compile all the analysis that you've done in a quick way so you can get right to the points that you want to address with the team. So it kind of puts it all together as a nice summary. So the compiled analysis will serve as a great summary that you can use for future documentation as well as for a quick review with your team to get their buy-in. So how is it that you can compile your analysis? Well, one method is that you can build a chart defining all the inputs, the tests that you used, and the test results. Now here's an example of one that you can use where you can compile it in just a simple spreadsheet. So to show you how this one shows how they're all laid out and within the spreadsheet is, you could identify what input was it that you were testing, the X that you were actually testing, and next you can identify the data source that you were using and the Y response that you might have been using, as well as the X factor that you might have specifically used within the test. So here are the factors you're comparing one against another. And the next section here gives you the test results, the actual output results that came from Minitab and how you might describe those. For example, you might say, here's the specific test you ran, here's the number of values that were resulted from that test, here's the p-value that came out of it, as well as the r-squared adjusted if that was relevant for that particular test, as well as you might be able to describe, give some little description of the results or visual display that might have come from the test, just as an easy reference for yourself. And then finally, a little further to the right, you might want to document your own conclusions based off of what you saw from the test. You might say, is it statistically significant, yes or no, and the practical significance and how confident you were. This might be something, again, like the r-squared value or your own judgment call of how significant you think it was. And then you might just add some narrative about your conclusions from this test. For this whole section, for example, is going to be testing on day of week. Well, here's the specific test that you ran, but you might have run a couple of tests. In this case, here's an ANOVA and the HOV, the test for equal variances. So you might have run a couple of tests, the test for the day of the week. So you might combine your conclusions in this way of how that one was. And here it's color-coded as green for any area that might be significant at all. Anything that's yellow might be, well, it may not be significant. And then anything that's red, you clearly know is not significant. So again, as a visual, at a high level, it gives you a great way to just jump to the things you know you need to address with your team, so you can kind of organize it in this way. And you can get them focused in on the ones you think are significant and quickly get them and their buy-in on the ones that you know are not significant that you can avoid looking at. Now, you have to be really careful here. It's so easy to get caught up in all the detail, the hypothesis tests, that you forget why you're even doing the test in the first place. You can easily get into what many people refer to as the analysis paralysis. But one essential thing I want to point out is that for every test that you run, you not only need to consider the statistical significance of the results, but more importantly, you need to assess the practical significance. So as you're working through some tests, you need to remember to follow a general order for testing significance. First of all, you first test for statistical significance. That is, it's often done by checking the p-value of the test result itself. So as an example, if you have a p-value that's less than the alpha risk, which generally might be like 5% or 0.05, then it's generally going to be considered to be statistically significant. For practical significance, however, this is where we might refer to something like the r-squared or r-squared adjusted value of the test if it's something that's available for that particular test. So as an example, if the p-value shows that it's statistically significant, then a high r-squared adjusted value could mean that how much of that statistical significance can be explained, that is, how practical that significance may be. However, even though you might have a very low p-value, that is, you're trusting that it is statistically significant, if your r-squared or r-squared adjusted value ends up being very low, you might say,
Yeah, it's statistically significant, but it really doesn't make much of a difference practically at all. So it's important to understand the relationship between how you'd interpret the results like this from a statistical significance versus practical significance. So no matter how you're interpreting your results, logic must always take precedent. It should be given greater weight and greater consideration, because if it doesn't make sense, if it's not logical, then maybe something is wrong in how you ran the test, or maybe there's another way you need to run it in order to validate it. So the results should not only be reliable, but they need to be logical as you input those into the equation. So as an example, you could have a regression in comparison of ice cream sales and shark attacks, where if you compare those, it looks like a p-value of 0. Yes, there's some correlation, and you might have an r-squared adjusted of 82%, indicating there's this very strong relationship between ice cream sales and shark attacks. As one goes up, the other one goes down. But that doesn't make sense. We wouldn't expect that there should be any relationship between the two. It might be some other independent factor that each of these are dependent on, such as summertime, which is why there would be such a strong correlation. So it doesn't mean they're actually related to one another directly, one causing the other. So you have to be careful of things like that. Or another example could be an ANOVA test that comes back with a p-value of 0.07 and an r-squared adjusted of 65%. Well, with a 0.07, we might easily say, well, that's above the 5% that we typically might have for an alpha risk. So because it's at 7% and it's above the 5%, we might just throw it out, assuming that it's not statistically significant, even though we might have an r-squared adjusted value that is generally strong or moderately strong at 65%. I wouldn't necessarily throw it away. Remember, we have to consider the alpha risk in comparison to the beta risk when we look at our p-value. In this case, when we have a p-value of 0.07, that falls within that gray area of the alpha risk at 5% and beta risk at 10%. In other words, we're saying it's not enough data to prove beyond a reasonable doubt that it is statistically significant, because it's not below our 5% alpha risk threshold. However, there is enough data to say that I'm not sure I can reasonably trust it. So it's enough data to say there could be a problem, but not enough to conclusively say there absolutely is a problem here, or it is causing some difference. It is statistically significant. So in this case, because the r-squared adjusted is so high as well, we might need to go back and collect more data, so you either get a p-value that is below the alpha risk of 0.05 or above the beta risk of 0.1 or 10%. That way we can be absolutely confident that there's either enough data to prove it is statistically significant, or we have enough data to prove it is not statistically significant because we haven't reached that beta threshold either. So it's important to not automatically assume something greater than 5% means we can automatically throw it out. Be sure that you account at least for that beta risk as well. Another example is a regression that might be between revenue and sales commissions that has a p-value of 0 and an r-squared adjusted of 77%. So we might think, hey, there's a relationship. Well, no duh, there should be a relationship between revenue and sales commissions. We would normally expect that as revenue increases, sales commissions, that's usually commissions for that revenue, are also going to increase. As revenue decreases, you're probably going to see a decrease in sales commissions paid out as well. So just understand that that's probably a test that you wouldn't need to run. You wouldn't need to do that kind of comparison, because we would expect there to be a relationship. Now, if you ran this and you found no relationship at all, then that's probably something worth exploring, to wonder why there isn't a relationship, because you would have expected it. But in this case, we'd expect it. The results came back just validating what we would have expected, so there really isn't any point to take any action on this, because it's not telling us anything new. So the bottom line here, just make sure logic dictates whatever path you go down. It should make sense, and with the things that you're comparing, make sure you're interpreting it appropriately. And if something does not make sense, then you should be able to retest it in other ways to confirm whether it's something that's worth taking action on.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to those metrics that you've been identifying before and running through the analyze phase for doing some of the hypothesis testing on a lot of those different statistical tests that were being reviewed. And what I'd like you to do is build a spreadsheet similar to the example that we had within this lesson for how you might document those results from those hypothesis tests that you might have run. You don't necessarily have to do everything, but try to select at least 3 of the hypothesis test results that you'd run and try to populate into the spreadsheet so you can get comfortable with the type of way that you're documenting it. And then try adding color to some of those cells so you can easily call out ones that are significant or ones that you know for sure or are not, or maybe ones that might need further explanation or not.
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hanson. Thanks for watching.